Hello everyone. I am a third year PhD student based in the Fourth Institute in Crete, Greece, and having a collaboration with Seya in Paris. So it's always great to be back. And I will be talking broadly about signal processing of IFU spectral data cubes, asking and primarily in the second half of the talk asking the question whether we can use deep learning to infer the star formation rate by taking into account the kinematics that we can get in these IFU cubes. Before delving into that particular scientific question, I would talk in the first half of this presentation about a major problem that we have for high redshift IFU observations, which is highly noisy data. So I want to talk about my first project on the deep and sparse denoising of these data cubes, where I benchmark different develop and benchmark different methodologies using wavelets as well as using traditional techniques, wavelet transforms as well as deep learning. So to do this, I use a multi-tiered approach of different types of data. Firstly, I developed toy models of rotating disk galaxies, and then I continue with mock IFU observations from cosmological simulations as a bridge between purely simple theoretical models and real observations from ALMA. And my data, as I said, is our data are PPV cubes, where each spatial pixel or spaxel has corresponds to a spectrum. For making the toy cubes, I've developed this software, which I couldn't think of a better name, but this is purely theoretical spectral cube generating software of rotating disk galaxies, where I have used a Cirsic profile for modeling the two-dimensional structure and an exponential profile for the width. And this is highly parameterized, where you can control things from the field of view, the spectral and spatial resolution, the orientation and the inclination of the galaxies in our field of view, etc. This is a GUI that I made just for more accessibility. And here you can see one of the, I don't think the companion galaxies are visible here, but we have a central galaxy and two very dim companions, which you can see on the moment maps. So an example of the data that we have gotten, that I've gotten from the software are these two, which is one here is resolved by the two-dimensional Gaussian beam that I've assumed. This one is unresolved by the Gaussian beam, and you can see a double horn spectra showing the rotational kinematics of our central galaxy and the companions. Um, so the software is well documented and it's pip installable, so there is that. We are focusing in this project mainly on super high noise regimes. So so lower than a peak SNR of 10, going all the way to 3, where you can see that the signal is highly obscured by this artificial colored Gaussian noise that we have overlaid on the data. The observational references that I use are are samples from the ALMA crystal survey. I focus on these two samples, as one is resolved by the beam, one is unresolved, giving us a good idea of how our methods will apply to real data. And I chose the data from the crystal survey because these are also observations of rotating galaxies. And you can see that the signal is moderate to highly noisy. And I'm also will be drawing comparisons with observation of markedly different physics of the W2246 quasar, which is not observation of a rotating galaxy, just to see how well our methods will generalize to completely different kinds of data. As a bridge, like I mentioned, I use the mock IFU cubes from the fire or feedback in realistic environment cosmological simulations, which are being worked on by our collaborators at the University of Connecticut, where they observed a W2246-like system, albeit without the diffuse emission surrounding the central galaxy. So the methods that I've worked on in our paper are two more traditional methods of PCA and then a blind source separation with ICA. But the ones that I will talk about in this presentation are the 2D, 1D wavelet decomposition denoising method, as well as the deep learning with a 3D unit. as what we observed in our research is that the traditional methods do not work very well with interferometric noise in IFU cubes. So firstly, for 2D 1D wavelet decomposition, I use an iterative soft thresholding approach. So if you have a spectral cube like this, we can, for brevity, I will be super brief because the first presentation of this session has introduced wavelet transforms. So you can take each channel of this spectral cube and decompose it into different 2D scales. And for each pixel in this 2D scale, we have a spectrum which can also be decomposed in using 1D wavelet functions. So it's just a multi-scale decomposition of our spectral cube anisotropically because the PP and the V are different quantities that we are considering. So this gives a multi-scale representation where uh, wait, yeah, where you here if you can see the decomposition of a cube with a central galaxy which is heavily obscured by noise, and we can clearly see our signal being dominant in some of the scales, where the noise is being dominant in some of the scales. So when we take our spectral cube into these wavelet space, we can apply a threshold and to remove the coefficients pertaining to noise and retain only the coefficients pertaining to signal, and then do an inverse reconstruction to restore our denoised cube back into real space. So I used an iterative reweighting approach where I do multiple steps so that the wavelet coefficients that are above this chosen threshold are like not reduced in amplitude, as well as the different iterations allow us to extract the residual signals of so that we can get the maximum amount of flux possible from our noisy cubes. Alongside this, I have I have written a very simple 3D UNet architecture with four encoder blocks, four decoder blocks with skip connections, which directly take our PPV cubes as input and give us a denoised cube as output. And this UNet has only been trained on the toy cubes that I generated with my software. So now I'm going to jump into light mode to not blind you after so many dark backgrounds. First, the benchmarking of the toy cubes, we see that the UNet is dominating as a supervised denoising method, even in low peak SNRs of 2.5 to 3. The wavelet method does not do very well for very low peak SNRs because the flux is completely lost in the noise and there is no way of statistically differentiating between them. But for a peak SNR of 6 to 8, which is, let's say, moderately, still highly noisy, but more moderate to high level of noise, the wavelet method starts working almost as good as the UNet, at least for the resolved sources. We see that for the recovery of the spectral shape of toy cubes, the UNet does better, especially in the moderate weak SNRs, and the wavelet method initially struggles but attempts to recover the spectral shape. We have also done a very cursory hallucination quantification using apertures with hierarchical dendrograms, identifying the regions of similar emissions. And we observed that while the UNet is prone to hallucinations in the spectral channels where there is less amount of flux, where the flux is lost completely in the noise, but in any case, the wavelet method has very less number of statistical anomalies which would pass through our conservative threshold. So for what I can conclude from this is that for cubes which would have noise levels or SNRs that are higher than this, the wavelet method works as a very good interpretable method without any risk of hallucinations. So I've applied this with our ALMA crystal and the W2246 results data, and the results are great. I mean, nice because our UNet, which is trained completely on toy models or toy cubes, are able to generalize pretty well with data from crystal, which are of the similar which have the same physics as we assumed in our toy cubes. But for 2246, it is recovering 80% of the flux in the central galaxy, but since we have not modeled the diffuse emissions on the tidal tails that are present in this quasar, we can see that it's not able to model the diffuse emission outside the central galaxy. So which we can say that for future work, uh, okay, here I'm summarizing everything, but we can say that for future work, we can incorporate more complex physics in our toy cubes, so which can generalize more with other different types of observations, or we can use transfer learning to train a deep learning model with our toy cubes and fine tune on more task specific data. And also we can, future work would use uncertainty aware methods to reduce hallucinations, as that is a main bottleneck for units. So there are colleagues and collaborators who are working, I think, on these future goals now. But now, to not lose time, I would like to focus on the question of going beyond moment zero and using these, let's say, after pre-processing the noisy cubes, after denoising them, how can we extract more science from them? So if we can extract the star formation rate using both the spatial aspect as well as the spectral aspect of these IFU cubes that we have, because right now the scaling relations used to compute the SFR from observations of galaxies is use developing power law, empirically fitting power law relations using only the moment zero or luminosity maps. We want to see if the spectral information does provide any significant information about SFR more than what we could get from just luminosity. So this work is still in progress, very preliminary stages, and I would really appreciate if anyone has more any input on this. So please feel free to grab me in coffee breaks after this. And anyway, for this work, we are also focusing on the IFU cubes generated from the prior simulations. I think something is missing on top here. I had a heading. Uh, so this is also being worked on by our collaborators, where we have different emission lines for multiple galaxies, and we can have associated simulated physical properties computed from the simulations. So for example, this is the star formation rate, which would be the focus of this talk. I think I can scroll here, right? I think. Yeah, okay. So, and then in the heading, I just said that it's made from fire simulations, and this uses the Chimes chemistry solver code with the radiative transfer code RAD-MC3D to get realistic IFU observations that can be comparable with uh, ALMA observations, let's say. So for all these galaxies, we have multiple inclinations for which there are different radiative transfer runs and the associated physical properties for the same, leading us to have a large data set that can be used for, hopefully that can be used for deep learning. Okay, this is not very relevant to this, sorry. Yeah. So typically the papers on constraining SFR from galaxy observations are mostly in the global scale, but we would like to focus on estimating the SFR surface density from the IFU spectral cubes. So this is a brief flowchart of the machine learning methods that I've implemented. In the input, we have the number of samples, all the emission lines that have been simulated, and the features are both the moment zero or the integrated luminosity and four moments pertaining to the spectra that we have. And we are targeting the SFR averaged over 100 million years. So first, we try to reduce the spatial resolution to what is expected from from real observations. Initially, we get a highly resolved cube of 20 parsec per pixel, and I try to reduce it to around 300, and the spectral resolution from 5 kilometer per second to 20. Then I only choose the spaxels, which in our simulations have a star formation rate with above 10 to the power minus 2. And then pre-process, log scale, and normalize. And the machine learning methods are an attention neural network, a random forest, and XGBoost. This one, the attention neural network, is a more complicated model which uses one transformer block to compute attention, to learn the line ratios, if any, implicitly. And I have also compared it with these more simpler tree-based models to see if we are pointlessly overcomplicating things or not. One major bottleneck, those are the results are not very good. One major bottleneck is that since we threshold the pixels, the spaxels based on the expected SFR that we want, that is 10 to the, above 10 to the power minus 2, we lose a significant amount of spaxels. So the number of training spaxels end up becoming a couple of thousand, which is not enough to train a complicated neural network. So the results here are just marginally better than what we would get from just simple tree-based models. And also the number of unique galaxies is around like 20, which is not enough for training deep learning. But however, for seeing the attention analysis for our neural network, we see that most of the information of the emission lines that give rise to the SFR somehow are correlated with the O1 145 micrometer emission line. And if we do a feature important check, we see that most of the information is indeed still coming from the integrated flux and not the moments of the spectrum. For the tree-based methods, we observe similar feature importance results where the fine structure lines are giving rise to the SFR more, which makes sense because at high redshift due to dust attenuation, the infrared lines are able to provide more information about SFR regions. But regardless, I don't think this right now. This is a very final result as we do not have very conclusive, very good amount of data for training. So right now, I have data from these massive halo galaxies and the high redshift galaxies from FIRE. And what we are doing now is generating multiple snapshots of these galaxies. So multiple time evolutions of these galaxies so that we can have more unique samples for training as simulations at different redshifts would have different types of physical conditions and would generally work as unique galaxies as far as the machine learning models are concerned. So that is the state of results now, and I've summarized everything here. And in the future, once we have enough data, we would also try to constrain different physical properties like the metallicity, the gas mass, stellar mass, and not just the star formation rate. And right, thank you for the time because I think I overshot 5 minutes. Yeah.
No, you were good. You were good. Thank you. No, you were good on time. Think questions for Arnab?
So on your denoising of interferometric data, what kind of noise did you denoise? Is it just amplitude or is it phase and amplitude noise?
Sorry?
When you're denoising your
Yeah.
interferometric ALMA data,
Yeah.
what kind of noise do you try to, in interferometric data, you have two kind of noise, amplitude noise on visibilities and phase noise. And they do not have the same impact on your image. So when you're adding the noise in your simulations, what kind of noise do you add?
I think the amplitude noise, I add Gaussian noise convolved by the synthesized beam.
So thermal
Yeah.
noise.
Yeah.
Okay. Okay.
More questions? I have to say, when I heard the word hallucination from these models, it kind of scared me about how sensitive these things are and how much control when you do these artificial intelligence or machine learning models. I mean, how do you know you can trust the results or is hallucinating? I mean, we all have experience with ChatGPT.
Yeah. I think hallucinations are always an open problem with any machine learning approach. They can be improved upon with different kinds of models. But as we calculated here, the most of the hallucinations are in the extremes of the velocity range that we're having. So the majority of the flux is not hallucinating. It's being recovered very well. But yeah, I think about 4% of the total number of cubes are showing significant hallucinations in the extremes of the spectral cubes. So I would say, like, for most observations, which are like the ALMA crystal, like a peak SNR of 10 and above, the wavelet method is not hallucinating and you can trust them completely. But for machine learning, I think there should be more physically motivated data to train specifically for the task at hand. Like here, it's completely on the toy cube. So maybe if you train on the toy cubes and you fine tune it again with the specific kind of data you want to analyze, then we can reduce the hallucinations because the model will know what kind of data it is predicting, not just making assumptions from what kind of training it has.